Welcome back to Discrete Math. I'm Dr. Jeff Groh. Today we're going to talk about relations. First, recall that if A and B are sets, then the Cartesian product A cross B is defined by it's the set of all ordered pairs AB such that little a comes from set A and little b comes from set B. As an example of a Cartesian product, suppose A is the set ABC and B is the set 1, 2. Then A cross B will be the set of all such ordered pairs. A1, A2, B1, B2, C1, C2. The set of all ordered pairs where the first coordinate comes from the first set A and the second coordinate comes from the second set B. Another example would be something like R cross R. This would be the set of all x comma y such that x is a real number and y is a real number. In other words, this is equal to the set of points in the xy plane. So that's what you get when you take R cross R. You get the entire xy plane. A binary relation, or sometimes just a relation, from set A to set B is any subset of A cross B. So any subset of the xy plane would be a binary relation on the xy plane from the real numbers to the real numbers. So as an example, suppose I have these points in the xy plane. This would be a subset of the xy plane, and hence it would be a relation. Even if we took that oval and filled it in, it's still just a subset of the xy plane, and so it is a relation from R to R. A function from A into B, often denoted by F maps A into B, is a relation from A into B. So in other words, a function is a collection of ordered pairs. You have two sets. You have kind of this input set and an output set. And a function will be a relation. It will be a collection of ordered pairs. But in this case, we're going to require that these points in the xy plane satisfy the vertical line test. Such that if you have 2 points, x, y1 and x, y2, both an element of this collection of ordered pairs, which we're calling the function. Let's call this by a fancy name, a fancy f. So these 2 points are in there. The only way you can have 2 points with the same x value, and well, you can't have different y values. You can't have this. That would violate the vertical line test. So the only way these points can both be in there is if y1 equals y2. Equivalently, for example, suppose f is 1, 2, 2, 2, 3, 4. Is this a function? Let's plot the points. 1, 2, 2, 2, and 3, 4. This will satisfy the vertical line test, and so this is a function. As another example, suppose my relation is 1, 2, 1, 3, 4, 5. Is this relation a function? Well, let's plot the points 1, 2, 1, 3, and 4, 5. It fails the vertical line test, so this is not a function. But it is a relation. Sometimes we just talk about a relation on a particular single set. A relation on a set A is a relation from A into A, i.e., a subset of A cross A. A relation on a set A is called reflexive if the point A is an element of the relation. Let's call this relation R. And this is true for all A in this set. So for example, suppose my relation is 1, 1, 2, 1, and then 1, 2. Is this relation reflexive? Well, you can see that it has 1, 1 in there, and it has 2, 1, and even 1, 2. It's not a function, it's still a relation. But it's not reflexive because it doesn't have the point 2, 2. The 2, 2 is not in the relation. Therefore, this is not reflexive. If we take that last relation, 1, 1, 1, 2, 2, 1, and throw in 2, 2, this is now reflexive. As another example is the divides property on the set of natural numbers a reflexive relation? Well, let's see. Does A divide A? Well, yeah, every number except 0 divides A. 0 does not divide 0 because nothing divides 0. In other words, as long as we're on the set 1, 2, 3, and so on, the answer is yes. But when we try to extend this to sets that include 0, the answer will be no. So for n, yes. For other sets, no. A relation R on a set A is called symmetric if AB in the relation implies that BA is also in the relation. So you can only have note divides on the natural numbers, it's reflexive, but it is not symmetric. You can see 2 divides by 4, but 4 does not divide 2. A relation R on a set A is called transitive if AB is in there into the relation and BC is in the relation, implies AC is also in the relation. As an example, equal sign will be a transitive relation on R, the set of real numbers. You can see this because A equals B and B equals C implies A equals C. You should also note that not only is it transitive, but A equals B implies B equals A. It's symmetric, and every number equals itself, so the equal sign is also reflexive. Reflexive, symmetric, and transitive. In fact, that's going to be a special category of thing that satisfies all 3 of these properties. Is divides transitive? Well, if A divides B and B divides C, that does in fact imply A divides C. So yes. We've seen that divides is reflexive and transitive, but not symmetric. So it's not quite as special as the property of an equal sign. If you have 2 relations between the same sets A and B, then their union will also be a relation. Even more interesting is what we call compositions. Let R1 be a relation from A into B, and R2 a relation from B into C. Then the composition R2 composed with R1 is defined as follows. If AB is in R1 and BC is in R2, then AC will be in the composition R2 composed with R1. We think of this one going first and this one going second. We kind of think of relations as having more or less an input slot and an output slot. Not necessarily, though, because we don't have the vertical line test satisfied for all relations. But here, R1 acts first, and you have AB in R1, inputs A, outputs B. R2 then acts, and R2 inputs B and outputs C. So you have the input A, output C in the composition. If we have a relation composed with itself, there's a special notation that we can write, and that is R squared. We have this interesting theorem. A relation R on A is transitive if and only if the nth composition of the relation is a subset of that relation, and that's for all n in the set of natural numbers. This is an if and only if theorem, so in the proof we have to prove both implications. We're going to begin with the consideration of the implication this way. we'll suppose the conclusion is true, Rn is a subset of R for all n. Then in particular, R2 is a subset of R. Consequently, if AB is in the relation and BC is in the relation, then since the composition of R with itself is a subset of the relation, that implies then that AC is also in the relation. And that means we're transitive. We just need to prove the other direction, assuming transitive and implying the nth composition of R with itself is contained in R. To prove the other way around, we need to prove an infinite sequence of statements. N equals 1, N equals 2, and so on. And it seems the appropriate method for proving an infinite sequence of statements is math induction. Well, is R contained with R? And the answer there is obviously yes. And in fact, for this particular proof, we will need strong induction. So on part 2, we're going to suppose that R to the k is contained in R for all k going from 1 up to some n hat. So we get to assume this. And now we need to look at R to the n hat plus 1, which is R to the n hat composed with R. Now we already know all of these will be contained in R, so this will be contained in R, so this composition will be contained in R cross R. But that's R squared, and that is contained in R because 2 is in this list. And so we deduce then that the theorem holds. We're next going to talk about different ways of representing relations. And in particular, we'll start with the matrix representation. And I'll show you how this works. Suppose our set A is ABC. Then, and also suppose our relation on A doesn't contain everything in A cross A, but only some subset, namely AA, AB, AC, and BC. So one way to represent this relation is we'll have the inputs here ABC, the outputs here ABC, and we'll put a 1 in a cell if A, comma A is in the relation. AB is, so we have a 1 in this spot. We have AC in there, and also BC. Everything else will get a 0 because they're not in the relation. So we'll denote the points in the relation by this matrix. More generally, we'll denote the matrix M as follows. It'll have entries Mij, which means that this takes the form M11, M12 through M1n. Let's suppose A has n elements. M21, M22. So the first entry is the row, and the second entry is the column. First column, first row, second row. And so this matrix, which we'll easily abbreviate in this way, satisfies Mij to be 1 if the point AIBJ is an element of the relation, and 0 otherwise. As an example, suppose my set A has points 1, 2, 3, and B has elements 1 and 2. I'm going to define my relation to be the set 2, 1, 3, 1, and 3, 2. What is the matrix representation for this relation? Again, we put inputs here and outputs here. So 2, 1 is in there, 3, 1 is in there, and 3, 2 is in there, but nothing else. So our matrix will be 0, 0, 1, 0, 1, 1. Suppose we have M, and it is a matrix. The transpose of M is denoted by M with the superscript of T for transpose, and is obtained by reversing the order of the I and J. What does that mean? If my matrix M is 1, 1, 0, 1, 0, 0, M transpose reverses the roles of rows and columns. So you get 1, 1 in the first column, 0, 1 in the second column, and 0, 0. So while this matrix is 3 by 2, the transpose is 2 by 3. The first number represents the number of rows. The second number represents the number of columns. 2 rows, 3 columns over here. Recall that for a symmetric relation, if AB is in the relation, then BA is also in the relation. So we have the following theorem. A relation R from A into A is symmetric if and only if its matrix representation satisfies M transpose equals M. Such matrices are called symmetric. So you can determine whether or not a relation is symmetric by looking at its matrix. If the transpose of the matrix equals itself, then the relation is symmetric, and we say that the matrix itself is symmetric. We can also note that the relation is reflexive. We know that A comma A has to be in the relation, which means that all of the diagonal elements, M, I, will be 1 for all I. We next consider composition and boolean products of matrices. Remember, if we have two relations, R, which goes from A to B, and S, which goes from B to C, then S composed with R goes from A to C. Let's make some additional assumptions. Suppose the cardinality of A is, let's say, M. The cardinality of B is P, and the cardinality of C is N. Let's look at the matrix for the relation R. This relation will have m rows and p columns. It'll be m by p. The matrix for the relation S will have p rows and n columns. It'll be p by n. Which means that since these match, the product mr times, Boolean times, ms, will be defined and will yield an m by n matrix. It turns out that the matrix representation of the composition will be the matrix representation of R, Boolean times the matrix representation of S. Let me illustrate what I mean. For example, suppose the matrix representation of R is 1, 0, 1, 1, 1, 0, 0, 0, 0, and the matrix representation of the relation S is 0, 1, 0, 0, 0, 1, 1, 0, 1. Then the matrix representation of the composition S composed with R will be the product, the Boolean product of these two matrices. Let's see what we get if we take 1, 0, 1, 1, 1, 0, 0, 0, 0, and multiply it with a Boolean multiplication of 0, 1, 0, 0, 0, 1, 1, 0, 1. You usually multiply matrices by taking a row and multiplying it onto a column. So we'll take 1 times 0 plus 0 times 0 plus 1 times 1. The only thing you end up with there is 1. And the next product will end up with a 1 here and a couple zeros. We take the first row and multiply it by the third column to yield the entry in the first row, third column of the product. That also is 1. Now when we take the product of the second row with the first column, we get 0. The second row with the second column gives you 1. The second row and the third column gives you also 1. And then, of course, the last three are just zeros. In our next example, suppose our matrix for some relation is 0, 1, 0, 0, 1, 1, 1, 0, 0. I want to calculate the matrix representation of R squared, which is basically 0, 1, 0, 0, 1, 1, 1, 0, 0 times itself. Multiplying first, we have 0 plus 0 plus 0, and then 0 plus 1 plus 0. And then 0, 1, 0. Here we'll have 0, 0, 1, and then 0, 1, 0, and 0, 1, 0. Oops. And then 0, 1, and then 0. We next discuss representing relations using digraphs, which is short for directed graphs. So what is a directed graph? A directed graph is a set V of vertices called nodes and a set E consisting of ordered pairs of vertices. We're going to think of these ordered pairs of vertices as being like line segments from VI to VJ. So if we have a couple nodes, VI, and another node, VJ, this will be the directed line segment. It'll have a direction on it. We'll draw that in the center, typically. And so this will be a directed graph giving us the direction that this ordered pair occurs. And we're going to call these ordered pairs edges. So we're going to have nodes and edges, directed edges in this case. In this case, this is going to be the initial vertex, or the initial node, and this will be the terminal node. As an example, suppose our relation consists of the points 1, 3, 1, 4, 2, 1, 2, 2, 2, 3, 3, 1, 3, 3, 4, 1, and 4, 3. The coordinates are numbers 1 through 4. We'll draw these nodes in any random number of places in the plane like this. Now 1, 3 is going to be an edge. So we'll have the initial point at 1, the terminal point at 3. That gives us an edge going from 1 to 3. There's also one from 1 to 4. And from 2 to 1. We also have something that goes from 2 to 2. So that's going to start at 2 and end at 2 as well. From 2 to 3, we have an edge. From 3 to 1, so there's another edge going back, like this. From 3 to 3. From 4 to 1, we'll have another edge going this way. And from 4 to 3. So this will be the digraph representing this relation. How do you know whether a digraph is symmetric, reflexive, or transitive? Well, the digraph is symmetric if and only if every time you have points A and B, these as nodes, you'll have edges going in both directions. For every pair, when you have an edge this way, you have to have an edge going back. So if AB is in the relation, then BA is also in the relation. For reflexive cases, every time you have a node, AA must be in the relation, and so that's what the reflexive property looks like. They'll have a little loop on all of the nodes. And for transitive, you'll have to have 3 points, 3 nodes, A, B, and C. If A is connected to B with an edge, and B is connected to C with an edge, then A must be connected to C with an edge as well. That's how you detect whether or not the digraph is transitive.